Hello, everyone. It is Wednesday, December 15th, and it's time for the Knowledge Bolide Hangout sponsored by Topher Spin Meteorites. We are super pumped today because we have a special guest with us. We have the B612 Foundation and the executive director, Dr. Ed Lu. Ed Lu was previously a NASA astronaut for 12 years. He flew on both the Space Shuttle and the Soyuz spacecrafts. He's logged over 206 days in space, including a 6-month stint on the International Space Station, where he did a massive spacewalk to do some repairs. Dr. Lu continues his active research in the fields of science related to solar physics, astrophysics, plasma physics, and we have a plasma physics question coming up, cosmology, planetary sciences as well. Dr. Lu is the co-inventor of the gravity tractor. We have a question about this coming up too. So the gravity tractor is a tool that is used to change the trajectory of asteroids in a controllable way. So that's a very key point. Ed is currently the director of the Asteroid Institute, which is a program run by the B612 Foundation, where he is the executive director. I would like to thank the B612 Foundation and also Dr. Ed Lu for making time and making this possible today. So Dr. Lu, you have our full attention. Thank you so much.
So first off, thank you very much for inviting me. This should be fun. I'm going to tell you a little bit about some of the work that we're doing at the Asteroid Institute. Work on, as you guys would say, pre-meteorites, the stuff before it gets to the Earth. And I'd like to sort of tell you a little bit about why it's important that we track where these things are. So let me pull up a presentation. See if I get this to work. And hopefully you are seeing
an
introductory slide. Great. So this is about mapping the solar system. And what I want to tell you about is why that's important and what that means. So let me step back a little bit. This is a photograph taken from a car dashboard cam in Chelyabinsk, Russia in 2013. That's not the sun. That is an asteroid entering the Earth's atmosphere at a grazing angle, luckily moving mostly parallel to the ground. So this was sort of a rarer case. And the asteroid was about 19 meters across and had an explosive energy of about half a megaton. So very a lot of energy. Luckily, it went over the top of the city and actually didn't fully explode until it was well past the city, more than 50 kilometers from the city. And that's the only reason we didn't have more casualties. We had about 1,500 people injured, mostly by flying glass from shattering of windows. But we could have been looking at 1 million casualties had this been angled downwards and or closer to the city. Here's the interesting thing, or a little bit of alarming thing, is that there was no previous notice of this. And that is, in fact, the expected notice that we would get from most asteroids that hit the Earth, because 99% of them are untracked. We just basically have no idea where they are. We have an idea of how many total there are, but we don't have any tracking information on roughly 99% of the asteroids large enough to cause damage on the ground. So that cutoff is in the range of 20 to 40 meters ish. So therefore, if you're not tracking them, you actually expect no warning, right? And what does it mean when I say that 99% of the asteroids in the solar system are untracked? Well, that's the setup for what we're doing. I mean, what we are trying to do is build a map of the solar system. And it's not the kind of map that you might think about if you like a static map that you might draw on a piece of paper. A modern map is one that has more than just that information. And the other thing that's different about this is that every object is moving. So unlike a map of someplace on Earth where things are roughly stable, every object in the solar system is in continuous motion. So it's also in 3 dimensions. So when you add that together, this map of the solar system is a little bit different. And I'll like to tell you a little bit about why that's important. So let's talk about where things are in the solar system. So I'm going to give you a tour of the solar system, taken from far away here. So what I'm showing you actually is a view of the solar system, and along with the asteroids in the solar system. These are all the known asteroids. Okay, so this, where my cursor is right now, that's the orbit of Jupiter. We have Mars in here. We have the Earth in there, Venus and Mercury even in closer. Okay, so now all these trajectories are depicted accurately. So you can see that almost every object in the solar system is actually an asteroid. The green ones are the ones in the asteroid belt between Mars and Jupiter. These other ones, the white and blue ones, are what are called the near Earth asteroids. Now I'm zooming in on the Earth. You can see that there is just an awful lot of asteroids flying around there. And we'll get even closer. We're continuing to zoom in. You will actually see the orbit of the moon go by. You can sort of see it there. There it goes right there. And then we move in, you can actually see the disk of the Earth as we get in. This is a really interesting program. It's called Open Space. It's an open source routine that allows you to visualize anything that's in any of the NASA data sets. It's kind of neat. And wow. Again, what you see is that the solar system is almost entirely comprised of asteroids from a number standpoint. Total mass is dominated by the planets, but total number of objects is dominated by asteroids. In fact, each one of these things is its own little world, right? Going its merry way around the sun. It's kind of interesting to watch these things go here. You can sort of see the orbital mechanics at work. Things in closer to the sun are rotating faster. Things further out rotating slower around the sun, orbiting slower. So what we're working on is trying to figure out how we depict and make useful all the information of all the rest of these objects. It turns out, again, the real number of objects is about 100 times this. Okay, and that's with a cutoff of 40 meters. You know, something which is roughly the size of the impact over Tunguska in 1908. So what do I mean by a map? Well, there's two things that go into a map, a modern map at least. So first off, at the bottom there is sort of all the data that goes into it. Where is everything? And that's telescopic observations in particular, but it's not just that. So if you think of something like Google Maps, which I had the honor of working on for a few years when I was at Google, the map of Google Maps is not just the images. It's not just the images of the satellite images or the street view images or aircraft, airborne images, that sort of stuff. It is all of the services. It's all the calculational background that allows that to work. And what I mean by services, it's things like, at least for Google Maps, you're all familiar with the things that allow you to put a pin on a map at a certain location, or to get directions from where I am to, my favorite coffee shop or restaurant or wherever, to the ability to instantly zoom in or zoom out, or do any of those sorts of calculations, which happen in the background in a data center. And you combine all of those services with an observational data set, and you get a modern map. So in the case of the solar system map, what would that be? Well, that's determination of orbits from images. It's calculating if you know where an asteroid is at a given moment, where it will be in the future, because again, it's a dynamic map. So where are all these things going to be in the future? It is things like finding out if any of those objects has a chance of hitting the Earth in the future. And if so, what is the probability of that? As well as all the things that you would use for planning missions and those sorts of things. When you can build a whole series of services like that, combine it with the telescope observations, what you get is a space map. And that's what we're working on. So I'll come back a little bit to some of the uses of this, but I want to point out an interesting one right now. the first one that we're one of the surfaces that we are bringing out in the next few months is one called Thor, which is just an acronym for Tracklet List-Based Heliocentric Orbit Recovery. What does that mean? That means that it's a new way of discovering asteroids in data sets, because it turns out that the way we discover asteroids currently is we take 2 images of the sky separated by maybe an hour or so of the same area of the sky. And if an object is moving, it will actually have shifted a little bit during that period of time. And you can say, oh, that little spot that moved from here to here, that's an asteroid, perhaps. There's a lot of random points of light. Much of it is noise. So what they end up doing is they end up repeating that same area of the sky in the next day or two, again, with 2 images. And you look for something that lines up with the previous 2. And then for confirmation, you have to do it again. So you end up having to have 6 good images of the same area of the sky in fairly quick succession. And if you don't get, if any one of those is, for instance, weathered out, or for some reason you don't get good data, well, then all of those observations are lost. And what we've devised is a way to do this without that crutch of having to take the 2 images very close to each other. And we do this by enormous computation. What you actually do is you look at all the potential trajectories that an asteroid could have and say, does any of these random dots out there on a sky image, do any of them follow what would be a physical trajectory of an asteroid if there really were an asteroid there? And that requires an enormous amount of computation, but that is actually what we have, thanks to a very generous donation from Google, who has provided us with free computational resources in the Google Cloud. In doing that, we've actually been able to show that there are many, many asteroids in existing data sets, observations of the sky taken by astronomers, that they didn't even realize were asteroids. So we took a 2-week data set from a small telescope, and we found 10 asteroids that hadn't been noticed in that, just those 2 weeks thing, as a proof of concept.
Wow.
So then what we did, though, is we go, okay, that was just a very small telescope over a very short period of time. Let's take a big data set. There is a data set, they just changed the name of it. It now goes by this unpronounceable name of Neuer Lab Source Catalog, or the NSC catalog. But it's 7 years of observation from a number of different telescopes. And it's quite deep, meaning it goes to very faint levels of the sky. So you can see very faint objects in it. So that turns out to be, we figured there's going to be lots of asteroids in this, and it turns out, in fact, there are. So we took a 1-month slice of this data and ran it through our algorithms, and we found that we discovered nearly 1,000 new asteroids in just that 30-day slice of it. So what we're expecting to get over the next couple months as we grind through all this data is that we expect to have many thousands of discoveries, or tens of thousands of discoveries even, that we'll be making here. In fact, we expect that our little research group is going to be the most prolific discoverer of asteroids on Earth, and we don't even own a telescope, which is the interesting thing. So it turns out these things were hiding in plain view if you have enough computers. It's the basic thing. So what we're doing is we're turning this into one of our services. What are our other services? Well, services are like, if you can tell me where an asteroid is right now, I'll tell you where it's going to be in the future, and so on. Now, why is that important? Well, I make the argument that whenever there is a new frontier, that maps are the key to the opening of all those frontiers. So let's wind the clock back to the late 1400s, early 1500s. This map up here in the corner. It's one called the Cantino Planisphere. It's one of the very first maps drawn in 1508. And you can actually see, Africa. You can see part of the coast of South America. They didn't know it was on the rest of it. The Americas kind of, well, they had an idea it was there, but not really the shape or anything like that. Parts of Asia are in it. This is a remarkable map. It's in 1508. And in fact, at that time, all the great powers at the time, it was England, Spain, Holland, Portugal, Italy. They were all sending explorers all around the world to build maps. In fact, this map was stolen multiple times. As an interesting story, was there was a lot of intrigue behind this. It eventually was stolen and brought to Italy, and then it disappeared for several hundred years, only to be found on hanging on the wall of a butcher shop in Italy in about 1930 something, and that was when it was recovered. So it's in a museum now. But it'd be amazing to find. I wonder who has owned this map. But why did all those countries spend so much on building maps? And it was because they knew that maps tell you where the important things are. They tell you trade routes. They tell you it's a map for scientific exploration. They're very powerful things, right? They're the key to defense, the key to economic development, and the key to science. So you always build a map whenever you open up a new frontier. Here in the United States, after the Louisiana Purchase, the very first thing that President Jefferson did was to send Lewis and Clark out to go map the new frontier. And this is one of the maps from Lewis and Clark. Moving on from the current day, as I had mentioned, maps have changed significantly from these static maps to ones which are more like mapping platforms. This is Google Maps, but I think arguably it's changed the way people live. Arguably it has led to development of a lot of commerce, because companies no longer have to build a map in order to have a company that uses location-based information. So companies that you're familiar with that didn't have to build their own map, that built it off of Google Maps, are things like Uber, Lyft, Zillow. I mean, there's a ton of companies right now. And so mapping actually is a really powerful economic force too. So if you look off into the future and ask yourself, why would we want a space map? First off, I would argue that is the key to scientific exploration of space. It's the key to protecting the Earth from being hit by asteroids, because if you know where all the asteroids are, you know if one is going to hit the Earth, and that is the key sticking point in preventing us currently from being able to protect the Earth, is that we don't know where 99% of the asteroids are. So therefore, we cannot protect ourselves from 99% of the asteroids. And finally, for economic development, because again, if there is going to be development and commerce throughout space, and I believe there will be, then you really need a good map. And again, the key element of anything in space is where is it and where it's going. Where is it going? Because everything is moving. So I think this space map is going to be extraordinarily important. So where we are right now, we have a beta version of this map running internally, meaning just within our groups. Next year, we're going to make it available to some of the scientific community for doing things like uploading data sets and saying, are there asteroids in here that I haven't noticed, or things like that. And then really what we are doing though right now is we are preparing for the start of the most ambitious space mapping telescope ever built. And it's one being funded by the US government. It's called the Large Synoptic Survey Telescope, recently renamed the Vera Rubin Observatory. It's being built by the National Science Foundation, and it's going up on a mountaintop in Chile. In fact, this is it. This is a photograph taken a few months ago, this summer. It's being built, been under construction for some number of years. The main mirror is up in there. That this dome does rotate now, and they expect that first light will be in about a year and a half, followed by operations some number of months later. So this telescope is going to be amazing, because it is going to be the most powerful solar system mapping telescope ever built. What's different about it than most of the other telescopes is there's an extremely wide field of view. So rather than like looking down a soda straw at a tiny little slice of sky, it looks at an enormous area of sky. It's a $750 million instrument, so it's going to be interesting. It will discover. You don't have to read all the numbers. I'll give you the executive summary of this, which is that the Vera Rubin Observatory will discover about 10 times more asteroids than all other telescopes combined. So the rate at which we discover asteroids is going to increase very, very greatly, starting in about 2 years. That's the punchline. And even more importantly, again, you don't have to read all this. What is going to happen is that many of these asteroids that we discover are going to have a chance of hitting the Earth. In fact, about twice a week, we'll discover an asteroid that has a chance of hitting the Earth, whose orbit actually directly crosses through Earth's orbit at some point in the next 50 years. And that's going to be interesting, because what it's going to be like is, if you imagine each of these things as being a having a trajectory, but an uncertainty around that trajectory, so you don't know if it's going to actually hit the Earth or not. And that uncertainty is due to the fact that we can't measure it yet accurately enough based upon however many observations we have. Remember that if this thing does discover 10 times as many asteroids as all other telescopes, that means within a few years, nearly all asteroids will have been discovered, that we know of, will have been discovered by this telescope. And that means, sort of by definition, you will only have a short observing arc, a few years at most, that you have observed any of these asteroids, and that leads to a fair uncertainty in their orbits. And that means that we are going to be presented in the next few years with a lot of cases where we know of an asteroid and it might hit us. And that's why I think our space map is going to be very, very important, because it being open source, it's an open source project that allows others to essentially run their own versions of any calculations on this data, and to make the process of predicting whether an astronaut hits the Earth or not to be very open and transparent. I think that's going to be very, very important over the next few years. So you're going to be hearing a lot about this starting in about 2 years. So our mission again is to try and build this map of the solar system, not just for the purposes of protecting the Earth from being hit by asteroids, which I think is a good thing, but also for the development of commerce in space, and for scientific exploration, for understanding the evolution of both our solar system and our planet Earth, which is written in the orbits of the objects in the solar system. So that's a quick summary of what we're doing. I realize it's just been me blabbering away. So what I would like to do is see if you have any questions. Could be about this, could be about anything. Happy to discuss anything you folks would like.
The first question, we're going to go to Pat Brown. I have very little information about other questions, but this one has to do with plasma physics.
Sure.
And something we recently recognized on a meteorite. So, hey, Pat.
Wonderful presentation. Thank you. Very compelling story there, and amazing things to look forward to. So on some meteorites, very, very fresh meteorites, this was not very fresh, but a really, really fresh meteorite, we oftentimes see right when they land on the backside, and particularly for oriented meteorites, so they're not tumbling, they're,
one side forward, right?
Right. On the backside, we oftentimes see a thin film of brown, of a rusty sort of color. And I had heard it described as that, as you're transiting the atmosphere, you've created a plasma in front of the meteoroid, and 21% oxygen, or whatever the percentage is. That oxygen, being in the state of a plasma and very highly reactive at a high temperature, can actually combine with the iron in the meteorite on the backside and form a very, very thin layer of very exotic rust. Does that hold up to modern plasma science and physics?
Well, I don't know in this case, because the formation of that is also going to depend upon not just the temperature and the composition, but upon the flow field around these things, which I think is likely going to be different from meteorite to meteorite. So I'm certainly not an expert in this area. I can tell you that very, very high temperature oxygen and thousands of degrees, what you end up doing is you end up breaking up the oxygen from an O2 to a single oxygen. You actually break the molecules in half. And this atomic oxygen is extraordinarily corrosive. It does exist in low Earth orbit, and it's caused by radiation from the sun. Okay, and this atomic oxygen attacks most surfaces in low Earth orbit, such that if you don't have specially prepared surfaces, they tend to corrode very, very quickly, or form oxidation very, very quickly. And so, for instance, the paints on a lot of spacecraft, they'll discolor or just flake off, things like that. Familiar with this because they, you know, when they first launched spacecraft, they had them all shiny and whatnot. But you know, then it's up there, it's gone, you never see it again, right? But when they were able to go send things to go visit things that have been up there in space, or if you look at the outside of the space station, you know, early space stations, they were corroded. And you know, they've since found different materials to use so that they don't have as much of that problem. But you know, this is due to atomic oxygen, which I am assuming that kind of thing would happen on reentry also.
Right. Okay. So the opportunity is there, especially since it's very reactive, and there's some nickel, iron, metal, mostly iron.
Yeah. I would say possibly. Again, I'm not an expert, and I would think it would depend upon the particular case.
Right. Okay. Thank you.
Thank you. Awesome. Cliff has a question regarding, you mentioned in your presentation, commercial possibilities. So Cliff has a question regarding potential commercialization of this. Cliff?
Normally it's focused on defense to deflect an asteroid away from hitting the Earth. A meteorite collector in me is like, hey, what if we're going to deflect it anyway? Could we do so using, say, a gravity tractor or something? Could we do so with sufficient accuracy to actually nudge it into an orbit around the moon so we could exploit it?
Yeah, there's a lot
not just get rid of it.
Yeah, there's a lot of discussion of that. Now remember that when we deflect an asteroid, something like with a gravity tractor, or even like the DART mission, which just launched, the amounts of velocity change that we're giving to an asteroid is of order centimeters and millimeters per second. Okay, so you know, taken as a percentage of the orbital speed of something, you should be thinking something like 1/1,000,000th of 1%. So what that means is that these types of technologies are not great for bringing anything substantially sized, you know, into an orbit around the moon, in which case you have to change the velocity, typically by order of kilometers per second, many kilometers per second. And that's if you're very, very efficient about it. So, you know, we're down in the centimeters per second or millimeters per second, and we need to get to kilometers per second to do operations like that. Now, there was some discussion of doing that at one point, about 10 years ago at NASA. But the size of the asteroids they were talking about for doing that are, you know, really small, sort of like a car. So, you know, not large asteroids. So I do believe it would be possible with current technology, not large ones, not unless you got very, very lucky, in which the orbit was already very, 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 very close to grazing past the moon like that.
Okay.
Well, that leads me into my question then. With your work on the gravity tractor and the eventuality, hopefully, of these data sets that you're creating with known near Earth objects and the plethora that are hiding we don't know, how much time do you need in order to, or in the future, do you think that you'll have the ability to act and actually do a effective job of saving Earth?
Yeah, we do know that we can do this. In fact, you know, this demonstration mission called DART is going to do exactly that. It's going to deflect a small 160-meter asteroid by a centimeter per second or something like that. We're going to impart that to it, which turns out to be enough to make an asteroid miss the Earth if you have a few years notice. Call it 10 years or more notice. And that, in fact, our goal is our goal. Our goal is to have the uncertainty in these things small enough so that you would have 10, 20, 30, 40, 50, or even 100 years of notice. Okay, so that is the goal. If you find something which has less notice than that, in the rare cases that such a thing would happen, then you're going to have to either fly many kinetic impactors, you know, all at once, you know, hit it multiple times, or use something larger like some sort of explosive type thing, in the hopes that you can deflect it that way. The real best thing is to just build the map as soon as you can and not be in that situation.
Sue wanted to know, we all would like to know just a couple minutes, Ed, of your experience as an astronaut. What was it like to be chosen, and what was it like for your dream of becoming an astronaut to come true and to be out in space? Tell us a little bit.
Well, it was an amazing thing, I guess. I didn't set out to become an astronaut. I kind of became one by mistake in some sense. A friend told me that you're going to apply to be an astronaut, and that's how it happened. That was in 1994. I sent in an application, eventually got invited to come down to Houston for a week-long interview, like 8 hours a day for 5 days. That was the interview. And where you meet with everybody, do all sorts of tests, lots of tests. And then you go home, and eventually you find that they're starting to call up your friends, neighbors, and anybody you've ever worked with. And then on December 7th, which was Pearl Harbor Day, which was the anniversary of my selection, was just last week. But I was living in Hawaii at the time, and I know it was Pearl Harbor Day because every Pearl Harbor Day, they have a flyover to commemorate the attack. And my phone rang very early in the morning because I was in Hawaii and their time zone is different. And so they called up, and it was a guy named Dave Leesma, who was an astronaut, but he was head of the flight crew operations. So he was making phone calls that day. And he said, Ed, how would you like to come fly the space shuttle for us?
Wow.
And I was so shocked. I could not barely say anything. All I could say was, yes. That was my reply. And he said, great. Well, don't tell anyone yet, because we're going to have a press conference tomorrow. So you're not allowed to tell anybody. I'm like, okay. Hang up the phone, and I immediately dialed my parents, right? So to tell them, right? And everybody I knew. So, of course, I can't get hold of my parents. They were out Christmas shopping. So this is back in the days prior to cell phones. So I'm leaving them messages. Call me as soon as you can. So it wasn't until later that night they got home and called me. So that was the story of my selection. It was the best job I think you could ever have. Best group of people you could ever work with. Loved every minute of it, and spent 12 great years doing that. So I don't know what else. I mean, it was the thing you take away from it is what human beings can actually do when we work together. You put a lot of people together with a common goal, and you can do some amazing things. That's the real lesson I learned from it.
And I thank you for that. You actually spent 6 months in the International Space Station with not a whole lot of company either, did you?
No, it was me and one other person. We went to a series of skeleton crews. I was the first half of the first skeleton crew on board Space Station after we lost the Space Shuttle Columbia. It was an interesting time back in 2003. That ended up being my last mission.
Okay, so we'll ask another fun one then. And if anyone has another question, just put it in the chat. Ed, would you ever go to Mars?
I would love to go to Mars. I think my wife might forbid it. And we have kids here, and I think I would be in deep doo-doo if I said yes to that. So I may have to watch from the sidelines. Maybe one of our kids, our son or daughter, will want to do that someday. But I think my flying days in space are likely done, unless someday the cost comes down way a lot, such that I might get a chance to go again. I would love to take my wife up. Sure, what I used to do back in the day would be neat. Take my wife and our kids up.
Maybe when we have space hotels, she'll be more interested in going, more comfortable.
Maybe when the price comes way down. And I do mean way down.
We have another question. Topher, do we still have time for another one?
Sure, go right ahead.
Okay, hold on. The chat is moving. Okay, so this is from Ben. How do we deal with the ethics of a situation where we cannot deflect an asteroid from hitting the Earth entirely, but merely need to change where on the Earth it impacts? This is what we talk about with the geopolitical, right, Ed?
Yeah. I mean, if you have an asteroid's going to hit in a particular location, eventually, and you're going to move it out from hitting the Earth, it's, you're going to change its trajectory, but bit by bit, you're going to change it such that you're moving the impact point off the surface of the Earth. So you're always faced with this question of, for some very short period of time, somebody else is in danger. But, the situation you're talking about, which is hopefully you don't get yourself into, is one in which that's all you can do. I don't know how we would deal with that. The real key is, of course, again, early detection, because the earlier it is you detect something, the easier it is to deflect it, or the less impulse it takes to change the trajectory enough to miss the Earth. And it's like the 3 rules of real estate are location, location, location. The 3 rules of asteroid deflection are find them early, and find them early. That's 1, 2, and 3.
You were talking about the new observatory in Chile coming online soon, and that would be a great addition to your data points. Would it also be helpful to have maybe 2 other points of Earth covered, so they're looking out in different directions? Is one observatory all that's required, or would more funding and investment be needed?
Well, this one observatory, having additional observatories actually located here on Earth doesn't actually change things too much, because this thing gets a pretty good look at the sky. Well, you would want one in the northern hemisphere. This is in the southern hemisphere. Really, the big difference would be to have an observatory in a different location other than Earth. And so that is obviously quite expensive. There's been some advances in the last few years, which lead us to believe that you might be able to use much smaller telescopes, combined with very, very, very long exposure times. So taking long, time exposures and using enough computer processing to deconvolve out all that noise. Turns out that that is possible. So it might be possible in the next few years to actually have, instead of gigantic space telescopes, very small ones that can do this, and therefore very inexpensive. Not hundreds of millions of dollars, but perhaps hundreds of thousands of dollars. And that might make it possible to put a number of these out in the solar system to really do that tracking of all these rest of these asteroids. As powerful as the Vera Rubin Observatory is, it will not get us to that 100% coverage or even 90%. It'll probably get us to 20%. We're at 1% now. So it's good, but it's not the end of the line.
Gotcha.
Okay, maybe those space satellites have to do with this next question. This is Bruce. He wants to know if we have a blind side in seeing new asteroids emerging from behind the sun relative to where the current telescopes are aimed, or where Vera Rubin will be observing from.
Yeah, obviously telescopes works best when pointed on, when used at night, right? Or pointed away from the sun when you're up in space. However, it is a misconception to think that that is a blind spot, because what you are really doing is tracking something long enough that I can calculate its orbit. Okay, that doesn't mean, so if somebody's throwing a rock at my head and they're standing between me and the sun, and and that rock is only going in a straight line between there and me, then yes, I've got a blind spot. I don't want to be standing in that location. But remember what's going to happen. Remember, the Earth goes around the sun completely all the way around the sun every year, as do these asteroids. One of their years, which is somewhere between like half a year and a few years. Okay, and when I say predicting something 50 years in advance, that means the Earth is still going to go around the sun 50 times, as will that asteroid, very approximately, so many tens of times. And so you don't really think of these things as blind spots. I need to see that asteroid often enough so that I can piece together its orbit, regardless of which direction I'm looking. And in some sense, that makes almost no difference. I just have to see it often enough that I can calculate its orbit, is the answer. So, however, for those asteroids where you are unlucky enough that you only have a few months notice, then you do have a blind spot then, because it's, if it's coming out of the sun, then and it's going to hit you in a few months, then in that case, there's not really much you can do anyhow. So there are a couple of asteroid telescopes, notably one called Atlas, that are looking for asteroids just before they hit the Earth, meaning like a couple of days notice. With the idea, it's not for deflection purposes, not for protecting people, but maybe you could, in the case of very small ones, go look for meteorites, right? So this has been done before, right? There have been 2 asteroids that have been spotted prior to hitting the Earth. In one case, something like 72 hours, and one less than 24 hours. And they have recovered rocks from meteorites from the one that landed in Africa a few years back. And but in the case of the larger ones that you might see, maybe only something like a nuclear weapon or so, maybe you can evacuate an area if it's small enough. So that's their goal. Our goal is to actually step back a lot and give us decades of notice, not days.
And Ed, what about the next question is about the different compositions of NEOs from Ben F regarding telescopes and what they can find. What about NEOs that are not luminous, but instead are radiant? Can we see those objects?
Yeah, well, most of them are not luminous. I mean, none of them are luminous. They're all, we're seeing all of them in reflected light. Now, an infrared telescope can actually see the glowing infrared radiation off of these things because they're warm. They get warmed by the sun. But in general, you're really looking at reflected light from the sun off of these things. And most of them, unfortunately, are dark. They're sort of charcoalish colored.
This may be a needle in a haystack question, but have you ever recorded any data that would suggest impacting of asteroids together?
Oh, we know they hit. And the easy way to do that is when we go visit the larger ones, they're covered in craters. Right? So they hit each other, right? Mm-hmm. And the other reason that we know that they hit each other is that if you look at the size distribution of asteroids, for those who are mathematically inclined, it's what's called a power law, what's called a scale-free distribution. Looks like 1 over the size of the asteroid to some power. And that's what you get when you mix a whole bunch of things together and smaller ones come from collisions of larger ones. And the more smaller ones tend to collide more often because there are more of them, producing yet smaller ones. And when you have a situation like that, you get the kind of distribution that we actually see, which means they did come about from running into each other. How many of the folks here doing meteorite collection and so on also have come from an astronomy background, or are you more just is it more of like a geology type background, or is it more just like a gem collecting type? I mean, how do folks get involved in this? Well,
for me, it was learning that you can own them. I had no idea you can own them, and once I found out you can own them, I wanted to own them all. But there are a varied bunch of collectors, whether they get into it for the ultra science end of it, like Pat Brown does, or whether my wife likes pretty pallasites, or if there's people that want to, they may start out by seeing or learning about Chelyabinks, and that's what was the emphasis of their collecting. And what's great about it is we focus as a collector on any type of the meteorite collecting that we want: witness falls, historic falls, carbonaceous stuff, irons. It's really whatever suits your personality, and we have quite some different personalities in here.
Yeah, I mean, I love the thinking about when I hold a meteorite, the story that this thing has been through, right? You know, where it was maybe part of a failed planet, or if it's an iron one, well, it was in the core of a failed planet. Then it got broken up, and then it likely was orbiting the sun between, you know, in the asteroid belt. At some point, came too close to Jupiter, got flung into a different orbit, into the inner part of the solar system, and then eventually ran into the Earth and then got picked up, right? You know, if you think about that storyline of this thing you're holding, I just find that amazing.
Yes, especially when you put all of those mathematical things that had to happen, and then the likelihood of it falling somewhere where it was actually recoverable and then recognized and then made its way into science in our hands. So yeah, it's overwhelming when you think of in cosmic numbers, not human numbers.
Yep, exactly. Yeah. We had a neat experience of taking a group of our supporters down to Meteor Crater, which you can see behind Rebecca there, a couple of months ago. And as we were hiking down in there, it was kind of neat because there's fossils down in there. And I found a fossilized, it was like sort of a shell-like thing. And if you think of the story of that, not only was there a meteorite, an iron meteorite that came in and it dug up an animal that had been at the bottom of the ocean on Earth and then got buried and turned into a fossil, was well underground, and they got unearthed by that meteorite. So it was kind of, if you think about that story.
Rebecca, I think we may be running out of Ed's time. I don't want to step on his schedule too much. Was there any final questions that we had in the chat that were burning your eyeballs?
Well, there's a whole bunch of questions here, I see.
If we didn't get to your question, go ahead and email me, email us. We're happy to answer any questions that you have. It's been so nice meeting you guys all.
Yeah, I really had a blast with this. I'm so thankful for the whole B612 Foundation team, Rebecca and Danica, and of course, Dr. Ed Liu. Thank you so much for your time and showing why we should care and what efforts are being done to keep Earth safe.
And I want to thank you guys too. You guys have been awesome. And maybe one day we'll all meet in person someday and talk about meteorites.
That'd be fantastic. I have a small box coming your way, so hopefully I'll see you pimping my logo next time.
All right. You got a Martian meteorite coming my way? Awesome.
Yeah. I really appreciate your time. Thank you so much.
Thanks, everyone.